Okay, we can start with today's lecture. So, in between, after the last lecture, I have updated a little bit the website for the course. So now, if I go to the website, FR/predmet, what means course in Croatian, and after that mulsis. No, something's wrong. Mulsis maybe with Y, not I. You will see. Mulsis. This is the English version of the course. I have to log in. Okay. Obviously, there are still some internet, multimedia systems, multimedijski sustavi. So, the mulsus, sorry, that is the correct page name, mulsus. So this is the Croatian version of this multimedijski sustavi, mulsus. These sub-pages are now updated to wherever there was multimedia technologies is now changed to multimedia systems and everything else. And also about the course, o predmetu, I have changed this scoring information. So homeworks and laboratory exercises are now 15 plus 15 points. Attendance on the lectures is 5 points. Midterm exam 30 points, and final exam 25 points. Finally, we have also oral exam that is 10 points. The same is with the examination, classical examination, not this continuous assessment, but at the end of the semester, if you don't pass this continuous assessment based on midterm exam and final exam, you go to the conventional exam. There is one opportunity to pass the course in that way as well. And the scoring is the same as for the continuous assessment, but only now instead of having midterm exam and final exam, I have a single written exam with 55 points and oral exam with 10 points. I also have this updated information about the literature. So this course book is very useful. It is called Fundamentals of Multimedia, second edition. Last year, due to this COVID situation, this book was available freely for free download. We are not that lucky anymore, so we have a copy of this PDF, but normally you would have to buy this book. It costs something, I don't know what, something like 67 euros, but we have a copy also on the department in paper for this book, and this book is very useful because it closely covers the topics that we are covering in the course. Okay, so that is about this updated version of the course web page, and if I go back, I will also translate this information, these sub-pages, in English language, such that you will have also the English version of the web page for the course. The notices, so news are shown here, and they are also in English version. So if I go, what I have to do, intranet, multimedia systems, I have to go to the main page, then I have to change to English, and after that I have this news, and in this news I have these announcements for the introductory remarks. So all about this information. You can also check here, so this live YouTube channel where you have this lecture streams is available right here. So if I move a little bit here, with slightly delayed version of me is now moving as well. Okay, so on this main page of this course recordings, the main page is this SOA live stream. You will have organized like folders or how they call it, whatever, playlists. We have some from previous years playlists, and these are organized based on courses. But this year courses are also, they have shortcuts from the first page of this video stuff on YouTube, video channel on YouTube. Okay, so that is about the additional information regarding the organization and materials for the course. But now I will skip to the actual presentation for today's lecture, and it is already opened in this PDF. Okay, so now we are continuing with the topic of digital signal processing and how this digital signal processing relates to multimedia system, why it was so important for the development of modern multimedia systems. This digital signal processing, more accurate description would be processing of signals in time discrete domain. So by processing the samples of the signals. But in a way, since these samples are treated as numbers, that was the reason why this term was coined, digital signal processing, because we are somehow processing digital numbers that represent the samples of continuous time signals. So that was the genesis of the terminology, digital signal processing. This processing can be done either using program solution, program-based solution, by running a program on a computer, taking samples from some AD converter based on some interrupt source, and then running a small routine that processes the input sample and computes the output sample that must be forwarded to the DA converter. But sometimes this software processing is not sufficiently fast if the data rate is very high. So for some multimedia signals, you cannot really do this software-based processing in real time. And in these situations, it is useful to have a hardware realization of these processing operations. And in this case, this hardware is dedicated or designed to facilitate this fast processing of high data rate sources. More or less, that is related to video sources. Because with video sources, the data rates are much higher, and software processing is capable only in offline processing. So if we are not required to do the real-time processing, I can do the offline processing in some tools on PC, and after several hours, I have processed my video recording that is only maybe 20 minutes long, but I have applied some very sophisticated encoding techniques to compress the video source as much as I could. But sometimes, if I have a mobile phone, if I want to record a live video and immediately stream this live video over the internet, it must be done in real time. So it cannot be done in some software processing way that takes time. It must be done really without losing any frames, without any delay. And that is a situation where I must use hardware processing solutions. Okay, so this digital signal processing, when it was developed as a theoretical field. As a theoretical field, it was developed in the 60s or 70s of the last century. Why? Because at that time, there was first computer that was capable of really doing this kind of processing. The advent of first computer was something in this 70s or 60s of the last century. And it was ideal platform for implementation of signal processing, because before that time, all processing was based on analog circuitry. So you had analog networks, and these analog networks performed desired operation on time continuous signals. So I had some input signal, it was time continuous representation, and I had dedicated circuitry networks that performed this processing. And of course, in this case, the maximum complexity of such processing was limited by the complexity of the circuit that performed this processing. And just to maybe give an example, concrete example, consider, for example, you want to design a low-pass filter. This low-pass filter, you want to cut some noise from the signal. And if this is the spectrum of the signal, then usually the useful part of the signal spectrum is contained in lower part of the spectrum, in lower frequencies. So if it is speech, then usually between 350 hertz and 3.5 kilohertz. So from 350 to 3,500 hertz, you have most of the intelligibility information in speech. So to understand speech properly, it is sufficient to transfer only this relatively narrow band. Only 3.2 kilohertz is sufficient to convey the information about what you said. It is called narrowband speech coding. So all these narrowband speech coders are usually tuned, they are adjusted to represent speech in this very narrow bandwidth. So from around 350 hertz up to 3.5 kilohertz. You definitely lose some information. What do you lose? You lose the spectral content of fricative voices. So fricative voices like S or Z, they have high frequency content. So they are really not completely contained in this narrow band. So they have frequency components going up to maybe 7, 10, 12 kilohertz. But nevertheless, if I simply cut them out, I do not lose the intelligibility. I still can understand exactly what the person was talking. I lose some information about the identity of the speaker. So if I process the speech in this way, that simply by cutting out all of the frequencies about 3.5 kilohertz, I lose some it is harder to distinguish whether person A or person B uttered the speech sentence, because some of this identity information is contained exactly in this higher frequency region. But regarding the understanding of the content, it is completely sufficient to have this part. So now imagine that you, instead of having a clean voice, you have some high frequency noise. And then this noise is distributed in this spectral region above the cutoff frequency. And then you would like to design a linear circuit that would pass only this part of the spectrum and attenuate this noisy part of the spectrum. And example of actual implementation of such low pass filter is shown on this scheme, with this electric scheme. It is based on 3 operational amplifiers. These triangles are the so-called operational amplifiers. And if I add few passive components, these here are resistors, these 2 are capacitors. So exact value of each of these resistors and capacitors is shown in this example. I get the so-called 6th order low pass filter. So whether it is low pass or high pass or band pass, it depends on the choices of the values of these resistors and capacitors. So based on the design, I can design any desired characteristics, either low pass or high pass or band pass, by selecting the proper values of these capacitors and resistors. Such implementation is called, for example, Salem key circuits. The configuration of this second order section, so these are actually a cascade of 3 second order sections, and each of these second order sections has this Salem key architecture. So it works perfectly, but it works only in the frequency range where these operational amplifiers can perform ideally as ideal operational amplifier. If the signal source has much higher frequency, like megahertz or whatever, then you would need to use operational amplifiers that are designed to operate in such high frequencies. So there are available such analog operational amplifiers, but they are, of course, more expensive than those that work only in this low pass region as we have with speech or audio. So more or less, analog processing of speech or audio was possible with such an active network. Why active? Because each of these operational amplifiers is a really active circuit, because it contains at least around 20 transistors. In a modern version, you would have several hundreds of usually CMOS-based, so complementary MOS-based FETs, implementing the operational amplifier operation. Okay, and now at first, the theory of digital signal processing was used only to what? To simulate such circuit. So I designed such a circuit, but I also wanted to check whether it would perform as designed. So I would simulate input source, like sinusoid or whatever, and then calculate all of the voltages in all characteristics points of this network using conventional network theory. So you apply a Laplace transform, you can find easily the transfer function from the input to the output based on the frequency response of each of the sections. Based on this modeling, instead of using the theoretical representation, instead of using Laplace transform on analytic representation of signals, what you would like to have, you would like to have a simulation if you only have samples of these sinusoids at the input, and compute what happens with the linear network if I simulate the input signal with waveform. And one very popular software that was used for network simulation, for analog network simulation, was called SPICE. It is still available nowadays. It is used for courses in electronics. You can easily enter the complete network like a textual description of schematic into this tool. You apply some input source, and you get the simulated output based on the simulated input. You can also play with the tolerances of individual components. So, for example, this resistor should be 10 kilo ohms, but maybe you have some 5% tolerance on this value, and you want to check what happens with the response of this filter if this value is not exactly 10 kilo ohm, but maybe 10 kilo ohm plus 5%. So all of this could be done in this simulation software. It was called SPICE. And the mathematical theory that was needed to implement this kind of simulation was exactly the digital signal processing theory. So it was used to simulate the operation of analog circuitry. Based on this simulation, you could investigate the effects of parameters, of different parameters, for example, tolerances of individual values of components like capacitors and resistors, on the proper operation of the whole circuit. How this circuit is described. So basically, the whole circuit, using the network theory, is described using differential equations. So you have the differential equations that relate what? Current and voltage in each of the points. So voltage in each of the characteristic points of the network, or current in each of the loops in the network. Differential equations that relate this voltage and current finally create a system of equations that has to be solved either analytically, so you use a Laplace transform to find the analytical solution, or numerically. And that is where this digital signal processing comes to form. So instead of using the analytical solution, you simulate what happens if this waveform is a sequence of samples. Okay? Some of these very important scientists that were, I would say, mostly responsible for developing this theory in these late 70s or late 60s were Professor Oppenheim, Schaffer, and Rabiner. More or less, early textbooks in digital signal processing are authored by these three guys. Okay? So the concept is the following. So instead of having continuous waveform, time continuous waveform processing using analog network, you take samples of this waveform. These samples are shown with these dashed lines. These samples are actually acquired through this A to D converter. And usually the samples are equidistant in time. So I have sampling period, and I take samples with this equidistant sampling period, capital T. And this sequence of numbers, x of n, is then forwarded to the algorithm, to the processing algorithm. And how this processing algorithm would look like, I can show, for example, more or less for the same analog structure that I have shown here, to simulate the operation of such analog structure. I would have a short program sequence that completely describes the operation of such analog structure. For example, this code segment would simulate the behavior of one second order operational amplifier. What it does is actually it models this second order system with a discrete system. This discrete, time discrete system is modeled using IIR filter. This IIR means infinite impulse response filter. This z to minus 1 is the so-called state of the filter. It is nothing else but a memory location. So I store the state, and this state more or less corresponds if I have this continuous system, to the output of the integrator. So if I have the representation of this linear network in the differential equations, then I have the integrators that implement particular part of the network structure. And this integrator, output of the integrator has state, given voltage at certain time. And this state is then, in time discrete case, converted to the memory location. So each of these memory location contains a state of digital filter, of time discrete filter. And how would I describe the operation shown in this block diagram? I have current states for the numerator. This here is the numerator of the transfer function. This part here of the difference equation. And this part here implements the denominator of the transfer function. So this part here of the differential equation for the time discrete system. And what it does, it simply takes this value from this state, multiplies by A1. It takes the input signal, multiplies the input signal by A0. And finally takes this state and multiplies this state by A2. It combines all three together, and I have the input to the numerator part of the model. And this numerator simply delays this Y signal by one step or by two steps, and multiplies this signal with either B1 or B2, combine these two, and I get the final output. I was wrong, so this part is the numerator, this part is the denominator, because this one has the feedback loop, and this one does not have the feedback loop. And actual implementation is then shown in software. So this here is actually assembly language of one particular processor that does this kind of signal processing in time discrete domain. This operation is really multiplication. So multiply mx0 register with my0 sign. Treat these two numbers as signed integers. And then add to this product another product. Add to this product another product of mx1 times my0. And then you repeat such multiply and accumulate operations, but of course you have to continuously fetch new arguments for this multiplication operation. So you take these arguments from some memory buffers, and what you do, you actually implement this differential equation for the digital filter. So with actual hardware, so this hardware is digital signal processor. It is shown here in some early version, DSP from Texas Instruments, 320, I don't know, 62, something like that. So it can implement easily such operations, and it is tailored in a way that it has the special unit, executional unit, that is capable to do this multiplication with accumulation in this MEC unit. So this, instead of having only arithmetic logic unit that is typically available on classical CPUs, these DSP processors, they also have a dedicated unit that is useful for implementing MEC operation, multiply and accumulate, MEC operation. And this MEC operation is done as a single cycle instruction in the instruction set of this DSP. So it is capable of taking two, let's say 16-bit arguments, multiplying these two values, getting 32-bit product, and accumulating this 32-bit product in 40-bit accumulator. This MR is a 40-bit accumulator because this 8-bit extension is used to be able to accumulate several such products without worrying about the overflow. So normally, if you multiply 2 with 16-bit numbers, you get 32-bit result. But if you want to add 256 such products, then you must have also this extension on the left side. So you add 8 additional bits on the left side to accommodate for accumulation of, for example, 256 products. Okay, so that is the digital signal processing. So what are let me check. So what are the disadvantages of digital signal processing? First of all, one of the main disadvantages is that you need AD and DA converter even for the most primitive operations, maybe just delaying the signal. You need AD and DA converter, and it costs, because this AD and DA must be of sufficiently high resolution to avoid quantization error. Finally, you also need a processor, this DSP, or maybe sometimes dedicated hardware solution, even for the most stupid signal processing operation. And this introduces additional power consumption, so it is not very efficient way, because this analog processing based on operational amplifiers can be really power efficient. So the power consumption of such network is really minimal, especially if you use CMOS technology for these operational amplifiers. In this case, if you have a processor running the algorithm, or maybe hardware, digital hardware, if you have AD and DA, then it consumes a bit more power. Nowadays, it is conventional to have all of this on the same silicon chip. Before, it was necessary to have AD as a separate component, DA as a separate component, and DSP in between. But nowadays, with this mixed signal processing, they are capable of producing, with this silicon technology, all of this can be integrated on the same silicon chip. So the very fine analog input that requires low noise and high linearity can be integrated with digital circuitry that implements the processing part. And finally, again, integrated with this DA converter that finally must convert this digital value back to analog representation. And to understand what is this accuracy that must be achieved. So consider, for example, that this is 16-bit AD converter. This 16-bit AD converter, then, for example, if I have the impulse dynamics plus minus 1 volt at the input of this AD converter, then I get these output codes. And these output codes are plus minus 2 to the power of 15. So plus 32,000 blah blah blah, minus 3 to 32,000 blah blah blah. So I get this range of output codes at the output of AD converter. But one step of this output, one least significant bit, how much does it weight? It is 1 over 2 to the power of 15 times 1 volt. So that is the actual dimension of one step. It is 1 volt divided by 2 to the power of 15. And this is a really small value. So because this is 32,000, I get around 30 microvolts. So the actual interpretation of one LSB value at the output of AD converter is maybe only 30 microvolts. And these 30 microvolts must be maintained noiseless, so noise-free. I must have really all of these contributing sources that are added as a noise here must be smaller than 32 microvolts if I want to achieve the highest possible quality achievable with this AD converter. So if I want to have the meaningful last bit value of the output of AD converter, I must have the noise sources, this US, whatever, noise sources. These noise sources must be lower than this 30 microvolts. And that is sometimes very hard to achieve, because especially if you have combined this mixed signal processing, so you combine digital circuitry and analog circuitry on the same silicon chip, then you have this crosstalk. So if I have this DSP here, this DSP introduces quite a lot of noise, electrical noise. that would be added to the input analog channel. And this noise must be somehow isolated or removed or reduced or whatever. So you must use different techniques how to isolate this analog part of the input from the contributions of digital noise generated by the digital part of the circuit. Okay? So it is not that trivial. And it took several years or maybe decades to really solve most of these problems to be able to implement very high accuracy analog circuitry together with the digital circuits. Okay. But what are the advantages of the DSP? First of all, the accuracy of operation is only decided or determined by the representation accuracy of these coefficients and by the representation accuracy of the state values. As I said before, imagine that the state values are stored as 16-bit 2's complement integers, and the coefficients are also stored as 16-bit 2's complement values. So I get the error, representation error, that is again 1 over 2 to the power of 15. That is the representation error due to quantization of states, filter states, or filter coefficients. So I have to represent this value not as an ideal real number, but as a closest fractional number to 2's complement in the 16-bit word. And due to this quantization, I introduce the representation error for the state, but also for the coefficient. But this is something that I can decide based on the design, based on the implementation. If I need higher accuracy, I would simply use double word here. So I would use the representation that encodes the state of the filter, not with 16-bit integer, but with 32-bit integer. The same is for the coefficient. But in that case, the multiplier would need to be of the higher accuracy, higher input width and output width. So I should be able to multiply 32-bit value state times 32-bit value for the coefficient. And the output is, of course, 64 bits. The full output of the product is 64 bits wide. So the multiplier is more complex. It can be simulated using several 16-bit operations to achieve this double data word accuracy. But then if you simulate this operation, you also lose the time efficiency, because you have a sequence of instructions that are needed to simulate the double word operation instead of using the native single word operation that is supported by the hardware. So based on the design, I can decide how accurate would be to represent the signal states and how accurate would be to represent the coefficients. And this value do not change with time. The problem with analog circuitry was that all of these values, this C and R, they were temperature dependent. So if temperature of the ambient increase or decrease, so you have this temperature coefficient. And the value of resistor, the changes. So it is not ideal at 10 kilo, but 10 kilo plus something or minus something based on the actual temperature of the room. The same is for the capacitor. So the values change with temperature. Also, they change with aging. So all of these components have the aging problems, and their ideal values changed. So this year, when I measured the resistor, it was really 10 kilo. But 1 year from now, it is maybe a few percent less or more. So this aging introduced this undesired effect on the analog network. All of this, it does not exist with the digital structure, because all of these coefficients are always the same. Once I enter the ideal values of these coefficients, they are the same forever. And as far as the noise and the crosstalk is concerned, these structures do not have the problem with this noise. How to describe this? So in the analog circuit, normally the signal flow is from the left to the right. So for example, this signal should not somehow go back into this node. But it is only for the ideal implementation. For the real implementation, you have typically some parasitic capacitance connecting each of the nodes with another node. So it is something that you cannot control. Maybe with the proper design, you could reduce this parasitic capacitance, these connections between different nodes in the network, but not completely eliminate. So all of this crosstalk always exists. Again, if you have a signal here, this is a high impedance point. This is the low impedance point because the output impedance of the amplifier is 0. It is ideal voltage source. But this here, this point here is the high impedance point. And if you have some noise that is, again, either capacitive, so electrostatic crosstalk or electromagnetic crosstalk, all of this can cause undesired signal in some nodes that is added to the network. In the digital implementation, such things do not exist because they would be something like one loop of the network would somehow affect another loop of the network because one loop in the network implements one of these second order modules. Normally, you have only the proper signal propagation. Output of the first second order module is used as the input to the second one, to the second stage. Output of the second used as the input to the third stage. But you don't have any undesired crosstalk between these stages because it is really software implemented. You don't have also these noise sources that are either electrostatic noise or electromagnetic noise adding to some nodes undesired inputs because all of this is ideally implemented as numbers. So these are the advantages. So advantages, finally, with this digital signal processing, you can do some processing that cannot be implemented in analog form at all, because there isn't such analog structure that could do such operation that you could do with the digital signal processing. So sometimes there isn't any implementation in analog form that will do the same thing or equivalent thing in time continuous domain. Program implementation of digital signal processing is usually sufficient for many applications, especially in the speech or audio range. Maybe for video signal, you should combine this software processing with hardware, dedicated hardware implementation for certain part of the algorithm. For other parts that are not that critical, you can still use program-based solution. Okay? Finally, if you have this program-based solution, the system can be easily adjusted to any new application. So if there's some new standard that is available, and the original system was designed for the former or the older standard, you can simply change the firmware by actually changing the software. So I change this software here, and after changing the software, this DSP, this software-based implementation, implements another standard, new standard. You don't have to change the hardware. The hardware is the same. You simply change the software that is run on this DSP. So you have this, flexibility of adjusting the hardware design to new purposes, to new functions. You can perform very complex signal processing, and what is also very important, you can do block-based processing. The block-based processing is very useful in some applications. So you don't process sample by sample. You take one sample and get the output sample. You actually take the whole block of samples. For example, 256 samples are taken as an input buffer. And only then you start the processing. It is typically used in spectrum analysis. So if I apply this discrete Fourier transform, I have to first acquire n samples of input signal, and after acquiring the whole block, then I can implement the digital discrete Fourier transform algorithm to compute the spectrum of the input block. And something like that, it was practically impossible in analog in time continuous fashion. Okay, this is more or less. So digital representation is, of course, more suitable for any storage or transmission requirements. If you have to transmit this media information at the end, or if you have to store it, then of course this digital representation is much more suitable. Okay, this is more or less that I wanted to say about digital signal processing. And as an example of the actual system, this here shows software, complete software implementation of analog processing of audio signals that normally required discrete components. So this audio processing, if you want to do the compressing or expanding of audio signal, then you had a dedicated device. It was called compressor expander. If you want to do the limiting operation for the audio signal, there was additional component, limiting component. If you want to do the equalizer, which means you want to emphasize certain spectral bands of the audio signal and maybe de-emphasize another band. So this was, again, a dedicated analog component that was used for this spectral processing of audio signal by having these kind of sliders that you move up and down and adjust the frequency response of the equalizer to compensate, for example, the acoustics of the room. And all of this can be completely simulated in software. So all of these operations can be completely simulated in the software implementation that runs on a PC. It takes the input from the AD card, from the sound card, and does all of this processing on discrete time samples taken from this AD card. After processing this data stream, you get the output stream. And this output stream is passed to the DA converter, and you get the processed output. And since it is all done in software, you can easily adjust any of the parameters of such system. So normally, with this hardware-based analog implementation, you had different potentiometers to adjust parameters of this analog processing circuitry. And these potentiometers are now soft-based. You have some knob, software knob, and adjust the value of some parameter to any desired value. So this is an example how this audio signal processing can be performed completely software-based. All you need to have is a conventional sound card in your PC and such software that simulates in real time all of these operations that are normally done with dedicated hardware components. Usually these are either analog, but they also can be digital components, digital-based components for the processing. Okay, now I'll make a break because we are 3 minutes after the 5. So if you have questions about this. Okay. Then we'll have break for 15 minutes. You also have this balcony here. If it is open still, I need to check.
we don't do homework or stuff like that.
What?
We just have the final exam and main exam has some project to do. Here, every exam is some project.
Actually, in Turkey, we do homework every week. So, I can understand the situation, but here, no, I don't want to do that.
So you want a new student?
Yeah.
Okay, so do you have any questions?
It's okay.
Okay. You missed this first part about the organization, but you have this recording also.
Okay.
So you can play this recording and you will have this information about the organization and the course and everything else. I will try to translate all of these sub-pages in English as well, so then you will have the real bilingual information as well. Okay. Okay. Dajte, može samo kolega jedan papir prazni, se svi potpiše, gdje su tu, ne, moramo raditi evidenci dolazaka. Samo jedan papir, ne, jedan popis, ne, da sve napiše ime i prezime. So I will pass one paper just to have the attendance record for today, because we get these 5 points based on the attendance. So you just write the date and your name in capital letters, and then you sign just to have the record of your attendance today. We have 2 colleagues online, so...
Potreban Jumbog ili...
Ne, ma ne treba. We don't have this Jumbog number, so only the name is sufficient. Okay. Another example of software-only processing is exactly this, as I said before, spectral analysis. So, for example, we want to do the spectral analysis of audio or speech signal. Then what you do, you are actually acquiring blocks of input signal. You are computing this fast Fourier transform. So this discrete Fourier transform can be computed in an efficient way using the so-called fast Fourier transform. And this fast Fourier transform is much more efficient because the complexity of the discrete Fourier transform is n to the square. So if you have n samples, you want to compute the DFT in n samples, so n spectral components, you have the complexity that is proportional to the n squared. But if you apply this fast Fourier transform algorithm, then the complexity is reduced to the n times logarithm base 2 of n. So instead of n times n, you have n times logarithm of 2 of n. For example, if you have 1024 samples, so to the power of 10, then this logarithm of 2 of 1024 is 10, of course, and then the complexity is 10 times 1000 instead of 1000 times 1000. So it is much less, 100 less complexity to perform fast Fourier transform in comparison to the direct implementation of discrete Fourier transform. And this example shows spectral spectrogram of speech signal. This axis is the time axis. This axis here is the frequency axis. So it shows how the frequency content changes with time. The amplitude is described or shown with color. So very high amplitude is shown with this red or even brownish color, while very low amplitude is shown with blue color. So the lowest amplitude is shown with the blue color. And what I see here, I see the structure, the spectral structure of one short example. So this here is time waveform, and I'm showing the spectral content for this short speech sentence, so short speech utterance. And what I can see this periodic structure of the spectrum. And this periodic structure of the speech signal is related to the periodic excitation of the vocal tract. So in our speech production system, the excitation comes from this glottis. So this glottis are these vocal folds. And these vocal folds are vibrating in the air stream coming from your lungs. So you push the air stream from your lungs through this glottis, through these vocal folds, and they vibrate. They intermittently close passage of the air and then open the passage of the air. So you have these pulses of air coming from your throat to your mouth. And in this vocal tract, these pulses are processed in a spectral domain, somehow, to do it described in the most easy way. So the vocal tract affects the transfer function. So sound frequency components of the input are attenuated, so they are reduced in amplitude, and sound frequency components are emphasized. They have a higher amplitude response, and this is called form and structure of the speech, because the way that vocal tract affects excitation is that some frequency regions are emphasized, or they have gain, a higher gain. Some different regions have lower gain, so they are de-emphasized. And these regions can be shown, I don't know, for example, here I have one formant, maybe here. So this is like a ridge where I have the higher gain of the vocal tract. And individual lines correspond to individual harmonics of the excitation. And these frequencies, this fundamental frequency of vocal folds, is around 60 hertz for male speakers, 60 hertz, up to maybe 300 hertz for little children. So for child speech, maybe would have a 300 hertz fundamental frequency. So these lines are more spread apart for the female voices or for the child voices. For male voices, these harmonics are more closer to each other. So I have a larger number of harmonics for male voices. But this shape is determined by the vocal tract, while these harmonics are determined by the frequency, or the fundamental frequency of vocal folds. Okay, so that is how I can do the processing, the spectral processing or analysis. Spectral analysis of speech signal that is completely software based. At the time, even before computers, there were devices that were capable of showing or printing spectrograms, speech spectrograms on some output paper, printer, and phoneticians were able to actually read what person said directly from this image. So they could see, I can see the vowel A here, or vowel E, or U, or some consonant. So they were capable, they were trained to understand this image as individual sounds that were produced during the pronunciation of some utterance. Okay, so what we have learned? We have learned that digital signal processing has very important role in multimedia systems. We have compared this digital signal processing to analog processing of signal, emphasized the advantages but also the disadvantages of digital signal processing. We have illustrated this digital signal processing for the case of filter structures, like low pass or high pass or band pass filter structure, if they are implemented using analog network or if they are implemented on a DSP processor as an algorithm. So this program-based implementation of digital filtration on DSP is very efficient way of doing the same thing, but it is much more flexible. Okay, now we will go to the next chapter, and next chapter is related to the digitalization or so not only it is sampling and reconstruction of digital signals or analog signals. So we are starting from analog time continuous domain. We are doing the time sampling, and then after this time sampling, based on these samples, I want to do the reconstruction, the reverse operation, to get finally the original analog waveform from which I started. So if this reconstruction is possible, and if this reconstruction is ideal, then I do not lose anything in time discrete domain. So I can do all this processing the same way as I will do in continuous domain, time continuous domain, but I do this processing on individual samples of these continuous signals. So I will now just show the basic requirements that are needed to be fulfilled in order to have this reconstruction capability. So I start from the continuous waveform, I sample this waveform, I take equidistant time samples, and finally I'm trying to reconstruct the original waveform from the samples. Okay? So we have these two basic operations. One operation is time discretization. Time discretization is actually related to this sampling process. I take the sample of continuous waveform. And beside this time discretization, I also have the discretization in value. This quantization is related to the fact that this AD converter has a fixed resolution. Just as an extreme example, let's consider that this AD has only 3-bit output. So that would be in 2's complement 0, 1, 2, and 3. So these are positive values. And negative values, -1, -2, -3, and -4. I missed this 2. Okay. In integer 2's complement representation, this would be -4, -3, -2, -1, 0, 1, 2, and 3. Okay? And if I simply divide this integer value with 4, I would get 0.75 as a fractional representation of this 2's complement number. So I have 3 possible positive values. I have 0, and I have 4 possible negative values. 0.25, 0.5 minus, -0.75, and -10. So that will be the fractional representation of 3-bit integer output, 3-bit 2's complement output. Okay, and this quantization is what? So all these values that are in between 0.125 or -0.125, are quantized with the same value 0. So if the value of input is lower than -0.125, and it is in between this -0.375, so this range would be mapped to this quantized value -0.25. And the same for the further possible values of the input signal. So the whole range of input signal is represented as a single value. This range as a 0, this range as -0.25. So I introduce error. And this error, if I do this rounding operation, is actually plus minus exactly this value, plus minus 0.125. That is the quantization error that I introduced by rounding this real value to the nearest integer of fractional representation with 3-bit 2's complement number. So the error, this 0.125 is actually 2 to the power of -3. So this word width directly relates to the quantization error. Plus minus 2 to the power of -3 is the error that I am introducing once I have to quantize the ideal real value with the nearest fractional representation for 3-bit value. And if I have 16-bit AD converter, so plus minus 32,000, then this is not 2 to the power of 3, then 2 to the power of minus 16. So the error is much smaller, of course. As soon as I have a high resolution AD converter, the error is much smaller. And that is the error due to quantization of value. So the amplitude is discretized. Amplitude discretization causes this quantization error, while time discretization is related to sampling process. So first, now we will consider this sampling. Okay, this sampling, in Croatian otipkavanje or uzorkovanje. So otipkavanje, uzorkovanje, sampling is a procedure where you convert continuous time signal x of t into set of numbers, into analog samples. But these analog samples with equidistant time sampling x of n are still ideal values, real values. So I do not do the quantization at this point. I only take the sample. So this x of n is the element of real numbers, not the fractional numbers as shown here. Conversion to sequence x of n is done by taking the values of continuous waveform in time instances Tn, and these time instances are simply integer n times sampling period t. I take sample each capital T seconds from the input analog signal. This n is the integer index for the time sample, where capital T is called sampling period, or 1 over capital T is the sampling frequency in hertz. Okay, this time discretization, this sampling, is actually part of the AD converter. So as an integral part of this AD converter is this structure that performs extraction of instantaneous value of analog signal at certain time instant. So ideally, it should be as if this aperture, this acquisition aperture is 0. So consider this is this x of t. So ideally, I should take exactly this value of continuous function at some nt time instant, t equal to nt. It should not be average value of the input signal in some window. So in the actual implementation, it is usually as an average of the input signal in some time window. Some delta t is this acquisition time window, and the input device takes the average value of the input signal in this time window and passes this value as output value as some integer code corresponding to the actual voltage. But ideally, this delta t should be 0. So I should do the exactly like pinpointing the value at time instant t, not like an average value of the input signal in some region around nt. Okay. So this is the sampling. So sampling can be described as multiplying this continuous signal with a sequence of Dirac delta impulses. So this Dirac delta impulses is delta of t, delta of t minus nt. So delta of t is 0 or if t equal to 0, otherwise. So if argument t is equal to 0, then this delta of t achieves infinite value. Otherwise, this delta of t is equal to 0. This infinite value does not make much sense. But if I do the integration of this delta t over t, then this integral is equal to 1. So it has unit integral. So it is a distribution. It has unit integral, but infinite instantaneous value. So at this point, since it is extremely narrow, it is the width of this delta function is 0. So the height must be inf, in order to, after multiplying this 0 with inf, I get the unit area, the surface of this signal. It is just a limit case of a signal that is a pulse. So assume that you have a pulse, and then you change this delta t, and correspondingly change the amplitude A. So A times delta t must be 1. So that is a condition. And then you put the limit of this, and this delta t goes to 0, but still maintaining the area of 1. And then you get what? You get this Dirac delta impulse. So it is infinitely high and infinitely narrow. Okay, and if I multiply this input signal with such a sequence, so this is just a set of such Dirac delta impulses occurring at nt, n plus 1t, n plus 2t, and so on, I get the delta impulses that are scaled with the value of the signal. Okay? So each of these individual delta impulses is just scaled with the value of signal at that particular point. So I get here x of nt multiplied by delta of nt minus nt. I get here n plus 1t, x of n plus 1t multiplied by delta t minus n plus 1t, and so on. So this is the process of ideal sampling as mathematical concept. So this concept of sampling could be mathematically described as multiplication of time continuous input signal with such a sequence of extremely narrow and extremely high pulses. Okay. It is shown here, maybe here, where? Not here. Okay. Not here. Okay. Going further, so once I convert this x of t to a sequence of numbers, x of n, so these x of n are still real numbers, so they're not quantized in amplitude. The question is, are there two different analog signals that would give the same sequence x of n? So what is the condition of uniqueness of this representation? This x of n must be unique representation of signal. Because if two different signals x of t are mapped to the same sequence, I don't have this uniqueness condition fulfilled. Then the next question is, if I know I have this unique sequence x of n, is it possible to reconstruct original x of t without any loss of information? So with ideal reconstruction, I get exactly the x of t that I started from. So which are conditions that have to be fulfilled in order to have these two conditions satisfied? And the answer to this is the so-called Nyquist-Shannon theorem of sampling. Shannon-Nyquist sampling theorem, and these are these two guys. On the left side is Harry Nyquist, and Claude Shannon is on the right. So there, these two are authors of this Claude Shannon theorem, and this theorem says that in order to fulfill these requirements, it is sufficient to have the sampling frequencies that is at least 2 times higher than the highest frequency of the signal. So if I do the spectral analysis, if I analyze the spectral components present in the signal, and if this signal has some certain highest possible frequency, f max, then it is sufficient to sample this signal with 2 times f max sampling frequency, and I should be able to reconstruct the original signal without any loss of information. So this here says, so the sampling frequency must be adjusted to be 2 times larger than the highest frequency of the signal. Okay? So 1/2 of the sampling frequency corresponds to the highest frequency present in the signal. Okay. And translated, it means that in each period of the signal, you must have at least 2 samples. So because if the sampling frequency is 2 times larger than the signal frequency, It means that within one period of this highest frequency of the signal, you have exactly 2 samples. So these 2 samples for one cosine signal, these 2 samples might be plus minus 1. For example, I'm lucky, and I take the sample here, and I take the sample here, plus 1, minus 1. And I get the sequence plus 1, minus 1, plus 1, minus 1. Actually, it represents this continuous sinusoidal waveform. But if I'm not that lucky, maybe I take these 2 samples. 0, 0, 0, 0. All of these samples blue, so they are also apart the same period as these 2 samples. This sampling period for these 2 are the same as the sampling period for these 2. But I'm not lucky because I'm hitting exactly 0 values for the signal. So obviously, this is a limit case, and from these zeros, I cannot reconstruct the original waveform because this digital sequence is equal to 0 for each and every n. There's no way that I can somehow compute the original waveform, this black one, from the sequence of zeros. But this is the limit case, when the sampling frequency is only 2 times larger than the signal frequency. But if it is more than 2 times larger, then you have not only 2 samples, but you have maybe 2-point-something samples. And then these 2 zeros will slowly change to something, plus minus 1, then slowly change to, again, zeros. Then slowly to plus minus 1, slowly to zeros. So you get somehow you get like a changing envelope of this sample sequence. Envelope is intermittently very high, and then with time it changes to some small envelope value. Okay. This condition for sampling is shown also here in this example, where we have 2 signals, blue and red signal. And these 2 signals are sampled. One of these 2 is sampled with fulfilling this condition, and the other one violates this condition. So the other one does not fulfill this condition. Obviously, this red one, this slower one, is the one that fulfills this condition. Why? Because we have samples. So this is one period. From this here to this here is one period of the red signal. And then how many samples do we have? 1, 2, 3, 4, 4 samples in one period. So this is the beginning of the new period. Again, 1, 2, 3, 4. For the red signal, I have 4 samples per each period. For the blue signals, I have exactly the same samples. You can see that these red samples are also the samples of the blue signal. Minus 1 here, 0 here, plus 1 here, 0 here, minus 1 here. So the sampling of the blue signal would produce exactly the same sequence of numbers. Minus 1, 0, plus 1, 0, minus 1. But how many samples do I have for the blue signal? So in this interval, the blue signal has 3 periods. 1 period, 2 periods, 3 periods. And how many samples? 1, 2, 3, 4. 4 samples in 3 periods. So in one period, it is 4 over 3 samples per period. 4 over 3. Obviously, it is less than 2. There should be at least 2 samples per period, and this one has 1.333 samples per period. So this blue signal is undersampled. You can say it is undersampled. We don't have sufficient sampling rate to represent this blue signal. On the other side, the red signal is sufficiently sampled, so I have the sufficiently high sampling frequency in representing the red signal. Okay, and after reconstructing, by starting from this sequence of numbers, minus 1, 0, plus 1, 0, minus 1, and so on, I should get ideally what? The red signal. The ideal reconstruction from this sequence would be red signal. So this example shows what is known as aliasing error, aliasing in English. And this aliasing is actually mapping of the higher frequency region, folding of the higher frequency band over the lower frequency band. And this is what happens here. So this high frequency region of this blue signal is folded over 1/2 of the sampling frequency and creates false frequency that corresponds to the frequency of this red signal. So somehow this blue signal is folded over 1/2 of the sampling frequency back to the red signal, which is something completely different, but nevertheless it has the same sequence of samples. Okay, and this is called aliasing error. And this aliasing also happens for 2D sampling, so two-dimensional sampling. Consider here, this is an image of some brick wall. And here this spatial pattern, this dark whatever, brown and white pattern changes in x and y direction with certain frequency, certain spatial frequency. And this spatial frequency again must it has to fulfill the requirement for the resolution, and that is the number of pixels. So in image, the sampling is how many pixels I select along the row and column. If I reduce the resolution of this image to some lower resolution, I halve the vertical and horizontal resolution. I take only each second line and each second column from the original image, and I get this smaller image on the right. Actually, it is 3 times decimated in this example, not 2 times decimated. So I take 1 column and skip 2. I take again 1 column, skip 2. The same for the rows. So it is 3 times decimated from here to here. What do you get? Again, you can see it is a brick wall, but this brick wall gets some fringes. These fringes here, these darker and lighter regions, are so-called Moir pattern. So this effect is actually the same as you see here. Some high frequency content, so very rapid change from dark and light part of the image, is mapped to some low frequency. So the low spatial frequency means slow change along the x or y axis between dark and bright. So this slow change is this. So I get dark, bright, because I get the low spatial frequency due to this aliasing effect in the image. So this aliasing is manifested in images as this Moir pattern. If I do not have the sufficient spatial resolution, if I don't have enough pixels along x and y direction, I would have this effect of aliasing. Okay, and that is the reason, since all of these cameras, they have discrete resolution. As soon as you take image from your camera, if you have some regular pattern on your suit or on your shirt, this regular pattern can also interfere with the resolution of the camera. And you would get low frequency if I go forward or backward, because if there is an integer relation between the actual pattern here, spatial frequency of the pattern, and the resolution of the camera, how many pixels do I have to represent each of these patterns, you would get this like seal effect. When seal comes out of the water, then you have this flashing. So this skin of the seal flashes on the light, on the sunlight, for example. Then exactly the same happens with your shirt. So you look like a seal coming out of the ocean and flashing in reflecting sun rays. Okay. That is the reason when you should always wear a monotonic texture for your shirt or for your suit when you're going to TV studio. Otherwise, it will have this undesired effect of aliasing. Okay? Then finally about the reconstruction. So how should I do reconstruction? So I have this sequence of Dirac delta pulses, and each of these Dirac delta pulses, it takes one value of the original waveform. So these pulses are equidistant in time. And now the question is, what should I do with these pulses to get the original black waveform? So how should I do the interpolation? Of course, the obvious way would be, okay, simply take the lines, connect these pulses with lines, and I get some approximation of the original waveform. This will be called first order hold. This kind of interpolation is called first order hold, because zero order hold is something like this. This is the zero order hold. So I take this value and keep it the whole period. This approximation is obviously not very nice, because it is very crude. This green one, this is called zero order hold, is very crude approximation of the original black waveform. This blue one is much better, this first order hold. But it is still far from the original waveform. And now the question is there a way that I can still achieve this black line? And there is, mathematically, there is a solution. What you have to do, you have to, instead of using this line interpolation or constant interpolation, what you have to do is you have to put a special waveform on the position of each of the delta pulses. And this special waveform is simply scaled or multiplied by the value of this delta pulse for that particular sample. This waveform is infinite. This red waveform goes to minus infinity, plus infinity. And it is called sinc function. Sinus x over x, sinc. And so it is unbounded, unlimited. It goes to plus minus infinity. And if I combine such infinite functions, and I simply scale each of these functions with the value, with the corresponding value of the sample, I would get, by adding all together, I would get the ideal reconstruction. So I will try to show it here. So this sinc function is shown here. It has a value of 1 at origin. So for x equal to 0, this sinc should be equal to 1, because it is actually multiplied by the delta function of a given height determined by the sample value. So for that reason, this sinc is normalized to unit value at t equal to origin, to 0. And then it has this oscillating response, and this oscillating response decays hyperbolically, because you have this pt in the denominator, sinus pt over pt. So this over pt defines this envelope, that is hyperbolic envelope of this decay. And the periodic part, sinus pt, it actually defines that it passes through 0 at each integer multiple of capital T. So if this sampling frequency, capital sampling period, is chosen, capital T equal to 1, then this sinus pt passes through 0 at each integer multiple of this capital T. And that means that contribution of this red waveform is exactly 0 at all other samples except for this one. So it is exactly 1 for this time sample, and contribution of this red waveform is exactly 0 for all neighboring pulses left or right. But it exists here, so this is non-zero, and as well as here. So it goes to minus infinity. So it exists in between samples. So each of these pulses, this negative or positive, it will transfer the contribution of this pulse to the left or to the right. So it conveys this information about this middle value, about this value of signal x of nt. It simply conveys this information to the left and contributes in this superposition. So these infinite curves are superimposed one on top of the other. And by adding all together, you get exactly the black line. So there is a proof, mathematical proof, that you really achieve the ideal reconstruction if you start from infinite sinc function, and if you just scale and shift this infinite sinc function based on the value of the signal sample. So it is shown here. So this here is that this who would know what this is? It describes this procedure of interpolation. So this sinc function is shifted in time, positioned at each time sample, t equal to nt. It has the period capital T. This period of sinc function is this period here, this capital T. It must be the same as the period of sampling, okay? Sorry. And it is scaled by the value of the sample at time instance nt, so x of n. Time sample x of n scales this sinc function. And what you have the infinite sum. So all of these samples contribute to each t value. So each real t value is a contribution of all samples. So that is important because if I take some slice, that is some t value, I take some t value, let's say this one, t something, and plus 0.123 times t, whatever. So this fractional position in between samples. So this fractional position, this black one, is a infinite contribution of all samples at this time instant. So not only the first neighbor to the left, to the right, all the neighbors to the left, all the neighbors to the right contribute to the value at this time instant. Okay. So the natural question is, can we really implement such filter, such interpolation filter? Is it possible to really have a structure or a system that performs this kind of interpolation based on this red sinc curve? Not really. We can only approximate this interpolation, this ideal interpolation. It says here that in the actual multimedia systems, this conversion, this reconstruction procedure is performed in DA converters. But first of all, there is one problem. That is the causality problem. And causality means that this red curve is not equal to 0 either left or right. So this left part is critical because, for example, consider that you have you want to interpolate part of the signal. We are now here, and we have two samples here, and we want to interpolate this value. But as I said before, this curve, this red curve, is infinite. And that means that some sample here, it also has some contribution. Not very nice, but it also has some contribution at this time instant t. So irrespectively of the fact that this time sample is far away in future, I still have to acquire this value because this value contributes to the value of interpolation at this point. So this negative part, negative part of the impulse response is critical. And it must be limited to certain maximum delay, because otherwise I have to acquire all the samples up to plus infinity. And only then I can do the reconstruction. In the actual system, I cannot do this that way, because otherwise I have infinite delay. I have to take all the samples together, and only then I can do the reconstruction. Sometimes I have to immediately get the output analog waveform, maybe certain fixed number of samples delay is tolerable. let's say I tolerate maybe 10 samples delay for the reconstruction of 100 samples. Otherwise, more than that would be too much. So this part is limited. So to some maximum number of samples in the future that would be used to find the contribution of these future samples at this time instant. And that is a problem of causality. So I do not know the future yet. So I have to, if I want to know the future, I have to add a delay in between. Only that way I can say, okay, now I'm processing this part, but I'm already having this sample in the buffer. So I can do the real-time, let's say, delayed real-time reconstruction. Okay, that is the reason why this ideal function can be only approximated with the actual implementation of the interpolation filter in the DA converter. But nowadays, DA converters, they use a special technique what is called oversampling techniques. And with these oversampling techniques, they are capable of approximating this ideal function quite close. So they are closely resembling the ideal interpolation of the sinc filter. And how does this representation error manifest itself? So if I would create a signal in the spectrum that is very close to this 1/2 of the sampling frequency, it is called Nyquist frequency. For example, it is 0.95 times fs 1/2. Very close to this Nyquist edge. Then it is a problem exactly with this infinite length of the interpolation filter that must be close to infinite if I'm that close to the edge of the band. Why is this so? Because exactly as I said before, so if the sampling is only slightly more than 2 samples per period, I have this varying from 0, 0 to ±1. Again, 0, 0, ±1, slowly changing. The envelopes are slowly changing. And that means, right now, for example, this envelope looks like this. So I have +1, -1 here. Then it goes lower and lower. These samples are samples from the continuous amplitude cosine signal. But this cosine signal is sampled close to the Nyquist criterion, slightly above this minimum required frequency for the sampling. And that is the reason why I have such a behavior, because this is this cosine signal. And here, okay, it has a constant amplitude, but here it is sampled at 0 points, and here it is sampled at ±1. Okay, so you have this intermittent change of the ±1 sampling for the cosine and 0, 0 sampling for the cosine. And what you have to do, you have to somehow, in the interpolation process, pass this information from left to the right or from right to the left to have this unit amplitude where the zeros are in the sequence. So close to 0 values are in the sequence x of n, but this interpolation filter, this sample here, contributes at this point, and this sample here contributes at this point. So you get this contribution of samples that are far apart from the current sample, and these samples reconstruct the red curve. Okay, without this, it cannot remove this variation of the envelope. Without this contribution, this envelope would be changing as a blue curve. Okay, and this constant sign can be achieved if this frequency is at certain maximum frequency relative to the half of the sampling rate. And typically, for nowadays DA converter, it is somewhere around 0.9 fs half, maybe 0.95. So only 5% of the band, of the last part of the band, is affected by this kind of varying envelope at the output. But if the frequency is lower than that, this interpolation filter is capable of achieving the constant rate curve, constant value of the amplitude at the output of the interpolator. So the output of the DA converter is really constant cosine, constant amplitude cosine. Although the samples are plus minus 1, going to 0, again plus minus 1, going to 0. So these are the inputs going from your DSP to the DA converter. And DA converter is capable of converting this sequence to the rate continuous amplitude curve. Okay, and that is up to maybe 0.9 of the band. 0.9, 0.95, depending on the DA converter. Okay, again we have 3 minutes beside the full time, so we'll make a break. But maybe a short break, huh? So we end up earlier, huh? 5 minutes break, then we end up 10 minutes before 7. Okay, so the last few notes. So this kind of AD and DA converters that utilize these signal oversampling techniques are also sometimes called sigma delta or delta sigma modulator based AD converters or sigma delta AD converter. So all these techniques are useful in achieving almost ideal performance for the interpolation up to certain maximum frequency that is close to the band edge. Not exactly on the band edge, but maybe 0.95 to the band edge. So up to this frequency, the interpolator and input AD converter with the corresponding anti-aliasing filter, they perform almost ideally. So I would take a sinusoid, I would do the AD conversion, I would do the reconstruction by passing the same value to the DA converter, and the final waveform would be almost identical to the input waveform if the frequency of the signal is maximally 0.95 to the 1/2 of the sampling frequency. Okay? And of course, there is a delay. Delay is inevitable. So to achieve this very high accuracy of reconstruction, there must be a reconstruction delay, and it is typically 10 or maybe even up to 100 samples delay. This delay is not critical for application like broadcasting or speech reproduction in audio systems or music reproduction. It is not that critical if I have maybe 10 or 100 samples delay in reproducing the digital waveform that is represented finally as analog signal going to the power amplifier. But it is critical if you use this kind of AD and DA converter in a control loop where you have the feedback. And if there is this dead time in the feedback loop, this dead time can cause havoc in your system, in your regulation. In automatic feedback loop, if you have dead time caused by the delay of either AD or DA converter, then your regulator, your system is not working properly. So they must use AD and DA converter technologies which do not have such delay. So it must be zero, almost zero delay if you are using this control loop, feedback loop. Okay? Going further. So what we have learned about the sampling of the signals, what is the required sampling frequency, what is the requirement for the uniqueness of the sampling. So how high must this sampling frequency be in order to be able to reconstruct the original signal from the samples of this signal. And the answer to this was given by the Knight-Shannon theorem of sampling. And we have introduced how does this insufficient sampling frequency manifest itself. Either on audio signal, for example, so that would be this example here, where I have the mapping of one sinusoid to another. This blue is mapped to another frequency, to the frequency of the red sinusoid. Or in the 2D signal, two-dimensional signal, where this spatial frequency is mapped to some low frequency, and I get these patterns. I get these patterns, these fringes that are caused by the insufficient spatial resolution, insufficient spatial sampling. Okay? What we have also learned is how we can do the reconstruction, how does the ideal interpolation reconstruction filter looks like, and it is based on the so-called sinc filter because it has this sinus pt over pt. So this function is called sinc. Okay, now we'll pass to the next chapter, and that is the quantization, the amplitude quantization of signal. So beside this time discretization, another discretization is the amplitude discretization, because after having these ideal samples at the output of AD converter, typically in the process of coding, this output of AD converter is further quantized. It is reduced in precision. So the values are of lower resolution than the values that are at the output of the AD converter. So typically, this output resolution of AD converter is the so-called raw signal resolution, or the nominal signal resolution. So I cannot do better than that. But if I want to encode this signal efficiently, if I want to store it, if I want to transmit it, then I would probably quantize it a bit more. So I would I would reduce further the resolution of the representation of such signal, hopefully without losing the quality, hopefully without losing the fidelity, the possibility of reconstruction. So this process of additional quantization is a part of the signal coding with losses, because quantizing the ideal or nominal value of the AD output to some approximate value generates error, so losses. It is called lossy coding. But it is done in order to reduce the rate, so to have compression. Okay, in our course, we would only consider the first type of quantization, that is so far we will consider only first part of the quantization error, that is part of the AD conversion. And result of this quantization is a digital media signal of a nominal or full accuracy, which is also called raw signal. Raw signal is the output of the AD converter. Finally, in further processing, this signal is encoded into coded form, or encoded signal, and depending on the coder, we can either reconstruct the original signal without error, so this raw signal is completely reconstructed. So in this case, we are using some kind of lossless coding, that no losses are introduced in the process of coding. Otherwise, if I have an encoder that is not lossless, then as a part of encoding, I introduce additional error, and I cannot go back to the original raw signal, only to the approximation of something that either looks like original signal to our perception, or it hears like the original signal. So in accordance with our psychoacoustic model or psychovisual model. Regarding the quantization of the signal, most oftenly, especially in high quality representation of media signals, we are preferring uniform or linear AD converters. And this means that conversion from voltage to codes are really linear function. As I have shown on this table, for this trivial example, so this mapping between the input real value and the output quantized value is a linear function like steps. So if I would show this, it would look like sequence of rising steps. The x-axis is the input value, ideal input value. For the actual example, so this was maybe this code 0, 0, 0, corresponding to midpoint. And as I said before, all of these values from minus 0.125 up to 1 plus 0.125 were mapped to the same value that after reconstruction is 0 volts. Okay, 0 volts, because this one is 0.25 volts. This was 0.5 volts. Okay, this was minus 0.25. But as far as code is concerned, this was minus 1, minus 2, minus 3, and so on. Okay, so each of these two's complement output codes correspond to one of the output voltages. But when I say linear AD converter, it means that this function here is a linear function. So I have the linear conversion from the input values to the output codes. actual AD converters might have some deviation from this linear function, maybe something like that. Okay? So there is a differential nonlinearity that even some codes may be missed due to this nonlinear mapping. So the non-ideal DA converter might cause this kind of nonlinearity, that the conversion from the input voltage to the output code is not exactly linear according to this linear red curve. And this is considered as an error. So ideal DA converter or AD converter should always follow the red line. Okay, and then if I consider only this red operation, ideal linear AD or DA conversion, this quantization can be completely described using this simple mathematical expression. So I simply divide the value, the input value, with the step size. In this case, this x value here is divided with the step size. In our example, it is 0.25. Why? Because in this example, I said that from 0 to 1 or from 0 to minus 1, it is 0.25 volts. So that is the step size for one LSB, for one least significant bit. And what I do, I simply divide this input value with 0.25. In this example, let's consider the input value is minus 0.1. Then, by dividing this minus 0.1 with minus 0.25, with 0.25, I get, this is approximately what, 2 over 5, I guess, 0.4. So this 0.1 over 0.25 is like 2 over 5. So this is the same as 2 over 5, and this is 0.4. And this 0.4, rounding this value to the closest integer, is still 0. Okay, when I round this value, in this case it is minus, okay, minus 0.25, minus 0.4. Okay, and this value is rounded to the closest integer. Closest integer is 0. Okay, if this value would be minus 0.6, it would be rounded to minus 1. If this value will be above 1/2, it will be rounded to 1. Okay, but if it is between plus minus 1/2, it is rounded to 0. So this value minus 0.1 is mapped to this region of code 0 because it is within this range plus minus 0.125. Okay, so I first divide input value with the step size. I get the integer number after rounding, and if I want to go back to the original representation, I simply multiply with the step size. Okay, this 0 times 0.25 is again 0, because this 0 is the ideal value for this range. If the signal is in the range from minus 0.125 to 0.25, then this value should be represented as a value 0. But if this value is above this region, so the input value is not minus 0.1, but for example 0.2. So if I divide this 0.2 with step size, it is 0.25, that would be like a 4 over 5, and that is 0.8. And this is 0.8 after rounding, we get 1. Okay? So this is mapped to the code 1. And this 1, after multiplying with the step size times delta, it gives 0.25, what is the output representation for the quantized value. Okay, so that is the basic idea behind this mathematical expression. I take the real value, I divide the real value with the step size, I take the nearest integer with the rounding operation, and by multiplying this nearest integer with the step size, I get a quantized value. So this 0.2 is mapped to 0.25 because this is the closest representation for the value 0.2. Okay? And now, after describing this operation, it has a certain name. This kind of quantization has a certain name. It is called linear pulse code modulation. Linear pulse code modulation. This terminology, pulse code modulation, was inherited from the early times of coding, when there were alternatives to code modulation, was pulse code modulation. Alternative were pulse amplitude modulation, pulse width modulation, pulse position modulation, sigma delta modulation, or adaptive delta modulation. So these were different techniques how you could represent the real value using pulse, either by shifting this pulse in position or by changing the width of the pulse. Somehow you want to convey the information about the analog signal. This information can be conveyed by varying the position of the pulse. So based on the position relative to some reference point, it is the representation of the real value. Or based on the width of the pulse, it is the representation of the real value. In this case, the representation is the binary code. So this pulse code modulation is a sequence of bits, 0, 1, 0, 1, where this code conveys information about the value of the signal x of n. Okay? And that is the reason why it is called, well, why this technique is called PCM, or pulse code modulation. Okay? It is completely characterized with two parameters. One is the step size. So what this delta, what is the value of delta? In this example, the value of delta is 0.25. And it is characterized by the total number of quantization levels, this n. And this total number of quantization levels, in this trivial example, it is n equal to 8 total number of levels. So this n multiplied by the step size divides the range, the total range. So in this case, the total range is 2 volts, from -1 to almost +1. Okay, so this number of steps, there are 8 steps. Each step is 0.25 large. So 0.25 times 8, it is 2. 2 volts is the dynamic range, actually ±1 volt. Okay, so these two parameters, this step size and total number of levels or steps, are characterizing the linear PCM converter. So this range from the lowest to the largest input value of the voltage is equal to the product of n times delta. In this example, it was 8 times 0.25, so this range was 2 volts, going from -1 volt to +1 volt. This range is called input dynamics of the AD converter. Input dynamics, and this input dynamics must be adjusted or the same, or it must be suited to the range of the input signal. So this input signal must be amplified with the proper amplification until it is exactly in the range of the input dynamics of the AD converter. Otherwise, if it is of a lower amplitude, then you are losing certain codes. So you never get, for example, 3 and 2, because the signal is always either 1, 0, or -1. So the signal level is too close to 0, too small amplitude, and we are losing actually the resolution. So instead of having 3-bit resolution, I am actually having 1-bit resolution, almost 1-bit resolution. So the idea is you must always adjust the input signal level, the input signal dynamics, to the dynamics of the input of the AD converter, to utilize all of the codes of the AD converter from the minus full scale to plus full scale. Nevertheless, you should never exceed the maximum or minimum value, because otherwise you have the clipping effect. If the value is lower than this -1 volt, if it is, for example, -1.5 volts, it will be represented as -1. So you get large error. The actual input voltage is -1.5 volts, and you get the representation that says it is -1 volt. It is the same on the upper side, so maybe the input voltage was 2 volts, but what you get is at most 0.75, because this is the largest representation, largest positive integer. In this case, it is 3, and you have this clipping error, because there is a maximum positive value that can be at the output of AD converter, and this maximum positive value is defined by this range, dynamic range. Okay, it says here. So the signal must be adjusted with its amplitude, and eventually this signal might also have the offset bias. If it is not 0, then you should adjust this signal offset or bias such that it corresponds to the bias or to the offset of the AD converter. This one has 0 bias, so this midpoint must be exactly 0 volts. So AD converter cannot represent values of the signal outside of the dynamic range, and this effect, when the signal goes outside of the dynamic range, is called saturation or overload or clipping. So it happens when the signal is either below the lowest possible input value, in this case -1 volt, or when the signal is above the highest possible input value, +1. Okay. For the actual implementation reasons, usually the number of quantization steps is the power of 2. So you have 8-bit converter, which means that it has 2 to the power of 8 levels, 256 levels. Or in this example, it would be B equal to 3. I have 8-level converter. What is 3-bit converter? So due to the actual implementation, usually this n is integer power of 2. Therefore, we can say that the output is a b-bit binary number. And this like B is also sometimes then called resolution of the AD converter. The same thing is also for DA converter. More or less, most of these things are also valid for DA converter. And in the case that input dynamics is A volts, then the step size is simply total input dynamics. In this case, it was 2 volts, divided by the number of levels. And that is multiplied with 2 to the power of -b. So divided by 8. In our example, if I have 3-bit converter, 2 to the power of -3 is 1/8, so 1/8. And I get that this step size is 2 volts. Divided by 8, I get 0.25 volts as a step size. This step size defines the granulation error of the quantization. So if I have larger step size, then this granularization error is larger. If this step size is smaller, then this granularization effect is smaller. Okay. And finally, it says that typically media signals are bipolar, so positive and negative, and that is the reason why we typically use the 2's complement representation in the AD converter and also DA converter. In that way, this 3-bit range is divided into positive part of the range, 4 levels for the positive part and 4 levels for the negative part, and representation is usually 2's complement. So typically this AD and DA converter, they would expect that for DA converter the input value digital must be in 2's complement format, as well as at the output of AD converter, the output value is in 2's complement format. Okay. For example, for the 8-bit converter, these codes at the output would be from -128, so this is 2 to the power of 7, up to 127, so 2 to the power of 7 -1. Okay, so a resolution directly limits the accuracy of AD converter. As I said before, all input values in certain range are mapped to a single value, to single representation error value, and this error is plus minus one step size. Plus minus delta half is the error caused by quantizing this real value to quantized value. Okay, in that sense, the operation of quantization is non-linear operation. It cannot be undone. So once I do the quantization, once I convert the real value to the integer value, I cannot undo this operation and get the original real value, because in this quantization I lose this fractional part. I do the rounding, whatever the fractional part was, I do not know later on. So I have only the integer part, this integer number, in this case 1, and I multiply this integer number with the step size, I get the quantized value. I cannot get back from this 0.25 to the original value of 0.2, so it is irreversible operation. Okay? And finally, we come to the point where we want to evaluate what is the effect of quantization in some measurable way. So we somehow want to model what is the effect of quantization on the accuracy of the signal representation. Okay? So we have to introduce some objective measure of quantization error, and one of such measure is simply ratio of signal variance and the variance of the quantization error. So these two variances, I will take the quotient of these two variances. And if I take 10 times logarithm base 10 of this quotient, I would get signal to noise quantization in decibels. So if I have this variance of the signal, this variance of the signal is denoted as sigma x squared. Sigma x squared. And if I divide this variance of the signal with the variance of the error, quantization error, sigma s squared, and if I take logarithm base 10, and if I multiply this with 10, I would get the error in decibels. And this error is called signal to quantization noise ratio, SQNR. Signal to quantization noise ratio that is measured in decibels. Okay? So this here is nothing else but the power of the signal divided with the power of the quantization error. When I take the ratio of these two powers, I get the relative relation between signal and error. And this relative relation in decibels is expressed as SQNR. So 20 dB, if I have 20 dB SQNR, what does it actually mean in ratio of these two squared values? 20 divided by 10, so this is actually 2. For this example, if the whole expression is 20, then this part here is 2. So what should be ratio of some two numbers? That the logarithm base 10 gives 2. The ratio must be 100, because logarithm of 100 is 2. So 10 to the power of 2 is 100, okay? So in order for this to be 2, then in this case the ratio of these two powers must be 100. So if the power of the signal is 100 times the power of the quantization, then we have 20 dB quantization error, or signal to quantization noise. Okay? If I have 40 dB, then this value must be 4. And this 4 means 10 to the power of 4. So the ratio of these two powers must be 10 to the power of 4. For 40 dB accuracy, for 40 dB quantization error. Okay, so how do we find how can we find these variances? We can treat the samples of the input signal as a realization of a random process X. In the same way, we can also treat the quantization errors again as a realization of the quantization random process E. So I have two random processes. One random process is the X for the signal, and another is E for the quantization error. This quantization error is difference between the ideal real value of the signal and the quantized representation. So in that example, it was 0.2 that is converted to 0.25 as a closest quantized value. So this difference is the quantization error. Okay, and in order to find these variances, what I have to do, by definition, what is the variance? I have to remove the expectation of this random variable X from X. Let's say mean value. I have X, but it has some mean value. And this mean value must be removed from X, such that it goes around 0. And after that, I square this debiased X value, and then find the expectation of this squared X. The same is for the quantization error. I remove bias. If there is any expected value of the quantization error, then I remove this E of small e, and then find the squared value of this difference, expected square value of the difference. Okay, and now to understand what this expectation means, we have to introduce this mathematical formalism that defines random processes and random variables. This E of something is the operator of statistical expectation. What does it mean? I have some example here. Okay, so by definition, this expectation of E is integral of E multiplied by PDF. So this is probability density function of E, and integrated over the whole domain of this E. So this E is a random variable. It has some distribution, and this distribution is described with probability density function Fe over E. Fe of E. And then if I multiply this Fe of E with E, and if I integrate it along the whole domain of this random variable, I get the expected value. And first of all, what this Fe of E is? It is like an extreme case of histogram. So histogram is much more familiar for you. For example, I take the input signal, whatever that is. Let's say this is my signal, and I ignore the fact it is a time signal. I only consider what are the values that I observe in this signal. So what are the values irrespectively of the position where they occurred. So what I do, I divide the signal into classes. Okay? And I ask myself, how many times is signal within this class? How many times within this class? So I count how many times signal was within the range defined by each of these classes. And what I get a histogram. So if I plot these classes here, first class, second class, third class, so this one is range, for example, this range here. And here I plot count, how many times signal has been in this range. So for each of the amplitude values, what I get is a count number. Okay? Count here is that much, count here is that much, count here is that much. So I get the histogram. And this histogram tells me what is probability that the value of the signal is between some two levels. This level and this level. So what is the probability that the signal is within two given levels? The width of this, the difference of these two levels defines this bin width. So how wide is this bin? If this difference is larger, then this bin is wide. And I count how many times of course, if it is continuous waveform, it's hard to count how many times. So first I have to discretize this waveform such that I have samples. And now I can really count how many times these samples were in one of the ranges, in one of the classes, okay? If I have samples, now I can really find the count number for each of the ranges, okay? And what will be the PDF? The PDF will be the limit when the bin size go to 0. So when I have infinite number of classes, and when these classes are infinitely narrow. So that is the probability density function. It is the density. It is always how many times divided by the width. So by definition, density is count divided by the range width. So if I put this range width to the limit 0, I go to the infinitely narrow bin width. I get what is the corresponding density of that value. So that is the probability density function. Probability density function actually measures what is the density of probability for certain value, because it cannot be probability. It is always the number of counts divided by the range. And when this range goes to 0, it can be only density, it can be ratio, okay? And once I have this probability density function for extremely narrow, for infinitesimally narrow ranges, now I can integrate this PDF to find the probability. So for example, I go finally to the limit case where I have this as a smooth curve, because this range is infinitely narrow. So for each value of x, I get the density fx of x. What is the density for that particular value of x? Okay, density is some value. Density can go to infinity as well. So it can be infinitely dense at some value x. It can be 0. Okay? Because it can be 0 if signal never reaches some value between below some level. Okay? Then the density can be 0. Okay? And once I have this continuous function, so I put this to the limit when this bin size goes to 0, now I can easily find the probability by integrating this fx of x in some range. What this gives? So what would I get if I integrate the probability density function in some range x1 to x2?
The probability of it being between x1.
So I get the probability that x is element of range x1 to x2. So that this real value of x is in between x1 and x2. I get the actual probability that value of the signal would be in this range of values. Okay? And this fx of x can be also integrated indefinite integration of this fx of x dx gives you CDF. And this CDF is so-called cumulative density function. Cumulative density function going from minus infinity to x. This is x prime. So if I integrate the density up to certain point x, I get the cumulative density function. And it starts from 0. It starts from 0 at minus infinity and goes to 1 at plus infinity. So plus 1 at plus infinity. Why? Because this is a probability density function which has a total integral of 1. So if I integrate along the whole range of values of random variable, then the probability, total probability that you observe any value is 1. So it reads out, so this is the total probability that you observe any input value from minus infinity to plus infinity, total probability is 1. And if I differentiate this CDF function at two values, x2, x1. If I take simply a difference between CDF at value x2 minus CDF of value x1, what do I get? I get exactly the same thing as here. This is nothing else but the integral from x1 to x2 of the density. So either I compute the integral of fx of x without bounds, x1 and x2, indefinite integral. How it is called in English. So when you have the integral without bounds, who would know? Mathematical expression. Okay, so you find this integral of fx of x, you get the CDF. And if you take the value of CDF at upper point minus CDF at lower point, you get exactly the integral in this region, when the x value is from x1 to x2. Okay? And that is the reason why we will continuously, in the remaining slides, very often we will be using this PDF. So this is called probability density function of a random variable. It is nothing else but the limit case of the histogram of this sequence. Okay, so I compute the histogram of sequence, and I allow these bins, these ranges, to be infinitely narrow, and I get probability density function. If I integrate this probability density function in some finite range, I get the probability that x is in between value x1 and x2. And this can be also found from the CDF, and this CDF is nothing else than integration of PDF from minus infinity to x. I get CDF of x, and I differentiate. If I take CDF at point x2 minus CDF at point x1, I get exactly the same value as integrated PDF from x1 to x2. Okay, so this terminology, this cumulative density function, this PDF, so this is cumulative density function, this is probability density function. These functions of random variable will be used. Why? Because we have to compute the expected value of a random signal, of the squared signal, or any other function of this random signal. For example, if I want to find the expectation of x, expected value, then that will be integral of x times PDF of x integrated over all values of x. If I want to find the expectation of x squared, I simply put here x squared. X squared times fx of x dx over x. So this is how the expectations are found. Expectations are found by multiplying the desired function of a random variable, for example x squared, with a PDF and integrating this product over the whole range of this random variable. And we get the expected value. So for example, consider that this fx of x is a Gaussian distribution around x equal to 0, symmetric. So what would be this integral? So what would you get if you multiply symmetric function, Gaussian probability density function, also called normal distribution? I multiply this by x, this is x, and I find the integral. What do you think we get? 0. Due to this symmetry. This part is symmetric to this part. And if I multiply this with negative line and this with positive line, then this cancel each other in the integral. They ideally cancel each other, and I get expected value of 0. So any symmetric distribution, the expected value of symmetric distribution, the symmetric PDF, is always 0. So around the point of the symmetry. If this point of symmetry is some value b, x equal to mu, then the expected value is mu. So if the symmetry is around mu, then the expected value is q. Is it the same as mean value? What do you say? What is the difference between mean value and expected value? And when these two would be the same?
Well, expected value depends on probability.
So the expected value is completely defined by the probability density function. But for some classes of random signals with a given PDF, the mean value, sample mean, is an estimate of expected value, expectation. Okay, we can estimate the expected value using sample mean. Which means I take a given number of samples from this distribution, let's say 100 samples. I take mean value of these 100 samples. I get something that is close to the expected value E of x, close. But this closeness can be biased or unbiased, and this closeness can be with certain variance. So I have certain error in representation, in estimation of the actual expectation. And this mean, sample mean, is the unbiased estimate for Gaussian random process. So if the random process is Gaussian, if I take 100 samples, then the best estimate for the expected value is the mean, sample mean. I simply take the mean value of 100 samples, I get the best possible estimate with the least variance to the actual underlying expected value defined by the PDF. Okay, because always, if I take a finite number of samples from a random process, I always approximate the parameter of the PDF. I approximate the expected value, E of x, I approximate the variance. I cannot know exactly what the variance was, what the expected value, what the expectation was. Okay? I can only approximate this value, and that is done by estimation. So I have the estimator of the mean, I have of the expected value, I have the estimator of the variance. Okay? Just some basic terminology that you must acquire or understand, because we will use it quite often in the remaining part of the presentations. Okay? So that is more or less enough for today. We have also exaggerated a bit than as announced. So see you next time, 1 week from today, at the same time. If you have any questions, you can also send them by mail or Teams, whatever. Any kind of communication is okay with me. Okay, we have 2 colleagues also. I have to write down their names just to know that they were present as well. Okay, then see you in 1 week time. All of this was in the course probability and statistics. Derivative statistics, probability and statistics. Basics of this are in that course, and also some of that was covered in the information theory course. So those that pass these 2 courses are in advantage. Bye bye. Jesi vi riješili šta za ovo?
Jesam, sad sam od profesora Patrića potpis dobio. Imam ovaj formular, samo ne znam gdje ga zapravo trebam.
Studentsku službu ja potpišem, onda moja studentsku službu nositi.
Ok. I bili smo možda mogli onda dogovoriti. Mislim,
bolje se hoćemo, da, možeš navratiti sutra.
Ok, može.
Ja se još ispuni, tu ne, ja divni sam da potpišem.
Ne znam da li imam kemijsku, ja imam ništa. Vi ste tu.
Suglasan želim na kmentora.
Da.
Dobro.
Do sutra onda mogu nakon ursa možda ili tako?
Može.
Ok, super, hvala.
pozdrav.